In this lab, I analyzed the motion of a falling object. The parameters set in this experiment include an object being at rest and then being dropped straight down, so there is no change in the position in the x or z direction. The object of choice was an orange stress ball with a mass of approximately 0.035 kilograms and a diameter of 0.07 meters. The ball was dropped at an initial position of 0,0.15, 0 Using the interval of 0.033 seconds, I calculated the initial velocity using the formula seen above, just so I had a reference point of how the velocity changed as time progressed. Similar to the first lab, I used Tracker to accurately analyze the motion of the ball as it falls to the ground. The ball's straight down motion was traced in Tracker, and the ball's position in the y direction was analyzed and plotted on a graph. This was done by tracking the center of the mass of the ball in each individual frame. The program then inserted the data into a table, and the graph shows a small initial change in position in the y direction, and then as time progresses, there's a greater and greater negative change in the y position. Then, I used GlowScript to create a computational model that predicted the ball's position in the y direction as time progressed. The code used to develop this model included using the velocity update formula, which is velocity final equals velocity initial plus the quotient of the net force and the object's mass times delta t, and the position update formula, which is the position final equals the initial position plus the velocity times delta t. The net force was inputted as the product of negative mass times the gravitational acceleration constant of 9.8 meters per second. Two models had to be created here. One that ignores the drag force in the air, which is on the left, and one that takes the drag force into account, which is shown on the right. The only difference in the codes for both models is that the proportionality constant for the magnitude of the drag force was incorporated into the calculations and code of the net force for the model on the right. On this slide, I charted the position versus time graphs for all three scenarios: the observed model, the predicted model without drag, and the predicted model with the drag force. I added trend lines for each graph so that the average slope of each graph is clear and comparable, because these lines equations and their slopes allow us to compare the velocity of the ball at different instances as it falls to the ground. For instance, the red graph with the red line has an equation of y equals negative 1.2879x plus a y-intercept. This slope shows that the average velocity over time was negative 1.2879 meters per second. The same can be done for the other two graphs, where the one with drag force had an equation of y equals negative 1.5226x, which was the slope or velocity in meters per second, and the yellow graph, or the yellow line, which shows the computational model without drag force, has a slope of negative 1.7963. As we can see here, the predictive model that does not take into account drag force actually had the greatest average velocity over time. So when analyzing the ball's predicted velocity with and without the drag, the model that takes drag into account best predicts terminal velocity, because it's when the velocity is constant, as the net force is zero, because the force of drag is canceling out the gravitational force. Speaking of terminal velocity, if the object was initially thrown downwards or towards the ground immediately after its release, then the terminal velocity would be different from the case where the same object was initially dropped from rest, because the magnitude of the velocity would be greater at the beginning of the time interval. All in all, the object's motion represents the momentum principle, because the net force is represented by the product of the object's mass and its acceleration, as stated in Newton's second law.